here, what is here? We have a loss function, and then we have something else which is called metric. So what is a metric? Well, it turns out that a loss function has, we have many requests or wishes for a good loss function. So a loss function should be a reasonable or an intuitive measure of quality of a hypothesis. And maybe the most intuitive quality measure is the 0-1 loss. So the 0-1 loss is equal to 1, so high loss, if, for example, a cat image is predicted by an artificial neural network as no cat. So here to the left, we have the predictions that, or weights that result in a hypothesis map that outputs no cat. So the output is no cat, but the input image was a cat image, so high loss. And here on the right, we say we output cat image, so correct classification, loss should be 0. So this is, in my opinion, maybe the most natural choice for a loss function for classification problems. This is called the 0-1 loss. 0-1 loss, and if you compute the average 0-1 loss and subtract it from 1, then this is accuracy. This is when you read accuracy, or AC abbreviated. This is 1 minus 0-1 loss. So I sometimes use synonymously 0-1 loss for accuracy, but it's 1 minus 0-1 loss. So 0-1 loss is high if there's a wrong prediction, so the accuracy is low. The 0-1 loss is small if there's a correct prediction, so the accuracy is high. So you always need to twist these definitions in your head. But for me, it's just easier to think about accuracy as a 0-1 loss. So why do you think we need to mess around and we need to torture ourselves with other loss functions? Why is this 0-1 loss not the ultimate loss function? It makes perfect sense. If we predict correctly the image, loss is 0. If we predict the image wrong, loss is 1. And if we average this over many images in the training set, we get a percentage, and we can say, let's say 99% of the image have been classified correctly. So makes sense to evaluate the quality of a particular hypothesis or predictor map using the accuracy. But why do you think we use other loss functions still? In particular, why do we use this why do we use this cross entropy loss? So why do we have here in this compile also this cross entropy loss, and not only we use the accuracy? There's one comment, a good comment. There might be a problem if the data set is not balanced. So if there's like 0.1% of cat images, but the rest is no cat image. Okay, but yes, that's one problem. So that's why the average 0-1 loss of the accuracy is not good. And you might look at something else like confusion matrix, which is a more kind of an upgraded or more fancy 0-1 loss. But let's say we have a balanced data set. So balancedness is not the issue. But why do you think it's not good, or it might be not so useful to use this loss function for tuning the parameters of the network, like the weights and the bias terms? So tuning, we want to, in the end, we want to tune the network parameters to find the minimum loss. So let's say we start here with the first guess of the weights. So let's say we are here. This is the first guess. Initialization, random initialization, we are here. Why is this 0-1 loss not so good to find the minimum? Derivative is 0. So we cannot really read out from this choice for weights in which way to go, because the derivative is 0. And that's why another loss function like this here, this blue is the gross entropy, is nicer because this has a curvature. It's tilted towards the minimum. So we can evaluate already for the first guess, which can be completely rubbish. The first guess for the weights can be completely rubbish, but still we can evaluate something called the gradient. We'll talk more about this in round two, in round two next week. And we know in which direction to go. So we can go one step, gradient step, to obtain the next one, better one. So we get a better choice for the weights. And then again, we look at the gradient and go down the gradient. Okay. That's why we want to use a smooth convex loss function. So a loss function with such a nice shape is known in mathematics as smooth and convex, but don't worry, we don't go into any more detail of convex analysis here. I just want to convince you that it's a good idea to not use the 0-1 loss for actually tuning the weights. For tuning the weights, trying out different choices for the weights of an artificial neural network, we use cross entropy loss, which is nice. We can use gradients to go down towards the minimum. However, the drawback of this cross entropy loss is that it's not very intuitive. What does it tell you if I report in a brochure of a machine learning classifier? So here's my app, I have trained it, and it has a cross entropy loss of 0.3. So what does the customer of this app or the user of this app now know about this this hypothesis? How well is it doing? Well, I would have no idea what this now means. A logistic loss value of 0.3. I would like to know what's the percentage of correctly predicted cat images. Is it 99% or 99.9999%? So when the final evaluation, the final kind of figures of merit that you want to put into the sales material for your machine learning method is the 0-1 loss. But for tuning, you don't want to use the 0-1 loss. You want to use something like a cross entropy. Okay. That's the reason why we choose here the cross entropy for the loss. And this loss function is used for fitting the model, for tuning the weights and the bias terms of the model.